Welcome to our journey through the cosmos, where we unravel the most mind-blowing theories of space and astrophysics. From the mysterious forces of dark matter and dark energy to the mind-bending possibilities of the multiverse and holographic principles, we explore the cutting-edge ideas that challenge our understanding of the universe. Join us as we delve into these fascinating theories, unveiling the secrets of the cosmos and pushing the boundaries of human knowledge and imagination. Dark matter. Dark matter is one of the most enigmatic and compelling subjects in modern astrophysics, constituting approximately 27% of the universe's mass energy content, vastly overshadowing the mere 5% made up of ordinary matter. This elusive substance first came to light in the 1930s when Swiss astronomer Fritz Zwicky observed that galaxies within the Coma cluster moved in ways that defied the gravitational pull of visible matter alone. He proposed the presence of an unseen mass, which he called dark matter. This initial hypothesis was further solidified in the 1970s through the pioneering work of American astronomer Vera Rubin. Rubin studied the rotational curves of galaxies and discovered that stars at the peripheries of these galaxies were orbiting at velocities that should have caused them to fly off into space if only visible matter were present. This suggested that an additional, invisible mass was providing the necessary gravitational force to hold these stars in their orbits. The current leading hypotheses suggest that dark matter could consist of particles such as weakly interacting massive particles, or axions. WIMPs are theorized to interact with ordinary matter only through gravity and possibly the weak nuclear force, making them incredibly challenging to detect. Axions, on the other hand, are hypothetical particles that could solve other mysteries in particle physics while also constituting dark matter. Despite their elusive nature, scientists have devised several ingenious methods to study dark matter. One such method involves gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Massive objects like galaxy clusters can bend light from objects behind them, creating a lensing effect that reveals the presence and distribution of dark matter. Direct detection experiments are another crucial approach. Facilities like the Large Underground Xenon Detector, located deep underground to shield from cosmic radiation, aim to observe interactions between dark matter particles and ordinary matter. Though no definitive detections have been made yet, these experiments are essential steps towards understanding dark matter. Additionally, computer simulations have played a pivotal role in our understanding of dark matter. By simulating the formation and evolution of large-scale structures in the universe, scientists can compare these models with astronomical observations. These simulations reveal that dark matter acts as a cosmic scaffold, guiding the formation of galaxies and galaxy clusters. Understanding dark matter is not just a theoretical endeavor. It has profound implications for our comprehension of the universe. The discovery of dark matter could lead to groundbreaking advancements in physics, potentially uncovering new forces of nature, or even leading to the development of new technologies. The quest to understand dark matter represents one of the most exciting and challenging frontiers in modern astrophysics. Each experiment, observation, and theoretical advancement brings us one step closer to unraveling this profound mystery. As we continue to probe the cosmos, the study of dark matter inspires scientific curiosity and drives technological innovation, pushing the boundaries of what we know and what we can achieve. This ongoing journey through the enigmatic world of dark matter promises to revolutionize our understanding of the universe and our place within it. Dark energy. Dark energy is an enigmatic and profound force that constitutes approximately 68% of the universe's total mass energy content, playing a pivotal role in the cosmos' accelerating expansion. Its discovery in 1998 by two independent research teams, led by Saul Perlmutter, Adam Rees, and Brian Schmidt, marked a significant shift in our understanding of the universe. By observing distant Type 1a supernova, stellar explosions that act as standard candles for measuring cosmic distances, they found these supernovae to be dimmer than expected, indicating that the universe's expansion was accelerating rather than slowing down. This finding suggested the existence of a mysterious force counteracting gravity, driving galaxies apart at an ever-increasing rate. One of the primary theories explaining dark energy is the cosmological constant, initially introduced by Albert Einstein in his theory of general relativity. The cosmological constant represents a uniform energy density that pervades all of space. Although Einstein initially posited this constant to achieve a static universe, he later deemed it his biggest blunder after the expansion of the universe was discovered. However, the observation of an accelerating universe has resurrected the cosmological constant as a plausible explanation for dark energy. Another theory is quintessence, which proposes that dark energy is a dynamic field that evolves over time, unlike the static energy density suggested by the cosmological constant. Quintessence could vary in different regions of space, adding a layer of complexity to our understanding of dark energy's behavior and properties. To deepen our understanding of dark energy, scientists have embarked on several ambitious projects. The Dark Energy Survey employs a powerful camera mounted on a telescope in Chile to observe and map hundreds of millions of galaxies. By analyzing the large-scale structure of the universe, DS aims to uncover insights into the nature of dark energy. Similarly, upcoming missions, such as the European Space Agency's Euclid and NASA's Wide Field Infrared Survey Telescope, are designed to probe the universe's expansion history and the growth of cosmic structures. These missions will provide critical data that could help distinguish between different models of dark energy, shedding light on this elusive force. Understanding dark energy is not only crucial for explaining the current state of the universe, but also for predicting its ultimate fate. If dark energy remains constant, the universe will continue to expand indefinitely, potentially leading to a big freeze, where galaxies drift apart, stars burn out, and the cosmos becomes a cold, dark place. Alternatively, if dark energy's influence increases over time, it could result in a big rip, where the accelerating expansion becomes so extreme that it tears galaxies, stars, and even atomic particles apart. Conversely, if dark energy decreases or reverses, gravitational forces might eventually dominate, leading to a big crunch, where the universe collapses back into a singularity. Despite significant advances in our understanding, dark energy remains one of the most significant puzzles in cosmology, challenging our grasp of fundamental physics and raising profound questions about the nature of space, time, and the universe itself. Scientists continue to explore new theories and conduct sophisticated experiments, pushing the boundaries of our knowledge. The study of dark energy drives scientific curiosity and technological innovation, bringing us closer to unlocking the secrets of the universe. As we continue to probe the mysteries of dark energy, each discovery offers new insights into the forces that govern our cosmos and our place within it, shaping our understanding of the universe and inspiring future generations of scientists. This ongoing journey through the enigmatic realm of dark energy promises to revolutionize our comprehension of the universe's fundamental nature, highlighting the intricate dance between the known and the unknown that defines our quest for knowledge. Multiverse theory. The multiverse theory is a profoundly intriguing concept in modern physics and cosmology, suggesting that our universe may be just one of an infinite number of universes that comprise a vast multidimensional space. This idea springs from various scientific frameworks, each offering unique insights and supporting evidence for the existence of a multiverse. One of the primary sources of the multiverse theory is the concept of cosmic inflation, introduced by physicist Alan Guth in the early 1980s. According to this theory, the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. This rapid inflation could cause the universe to break into countless bubble universes, each with its own distinct physical properties and laws of physics. In this scenario, our universe is merely one bubble in a frothy sea of universes. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, adds another layer to the multiverse theory. According to the MWI, every time a quantum event occurs with multiple possible outcomes, the universe splits into parallel universes, each representing a different outcome. For instance, in one universe, you might decide to take a job offer, while in another, you might decline it. This interpretation posits that all possible outcomes of quantum events actually occur, but in separate parallel universes. This mind-bending idea suggests that there are an infinite number of parallel universes where every possible history and future is realized, challenging our classical understanding of reality. String theory, a cornerstone of modern theoretical physics, further supports the multiverse theory. String theory posits that the fundamental constituents of the universe are not point particles, but rather tiny, vibrating strings that exist in multiple dimensions. Some versions of string theory require the existence of additional spatial dimensions beyond the familiar three. These extra dimensions could give rise to a multitude of possible vacuum states, each corresponding to a different set of physical laws and constants. This landscape of possibilities, sometimes referred to as the string theory landscape, implies the existence of a multitude of universes, each with its own unique properties and physical laws. The anthropic principle is often invoked in discussions of the multiverse theory. This principle suggests that the physical laws and constants of our universe appear fine-tuned for life because we live in one of the many universes where conditions happen to be just right for life to exist. In this context, the multiverse provides a natural explanation for the fine-tuning of the universe, positing that there are countless other universes with different conditions, most of which would not support life. Cosmological observations also provide hints that support the multiverse theory. For example, the cosmic microwave background radiation, the afterglow of the Big Bang, exhibits slight variations in temperature that could be remnants of interactions between our universe and other bubble universes during the early moments of cosmic inflation. Additionally, certain patterns in the distribution of galaxies and large-scale structures in the universe might be indicative of gravitational effects from neighboring universes. Despite the intriguing evidence and theoretical support, the multiverse theory remains highly speculative and controversial. One of the main challenges is the lack of direct observational evidence, as other universes, if they exist, would be beyond the observable horizon of our universe, making them inaccessible to current scientific instruments. Nevertheless, ongoing advancements in theoretical physics, cosmology, and quantum mechanics continue to refine our understanding of the multiverse, pushing the boundaries of human knowledge and expanding our conception of reality. The multiverse theory challenges us to rethink our place in the cosmos, suggesting that our universe may be just one small part of a vast and incomprehensible tapestry of existence, where countless other realities unfold in parallel dimensions. Each with its own unique story, this ongoing journey through the enigmatic realm of the multiverse promises to revolutionize our comprehension of the universe's fundamental nature. By exploring these theoretical and observational frontiers, we inch closer to understanding the true breadth and depth of reality, illuminating the possibility that our universe is just one of many in a grand, interconnected multiverse. Holographic Principle. The holographic principle is a fascinating and profound concept in theoretical physics that suggests all the information contained within a volume of space can be represented as a hologram, a two-dimensional surface, much like how a holographic image on a flat surface can display a three-dimensional object. This principle originated from the study of black holes and the perplexing idea that the information about everything that falls into a black hole could be encoded on its event horizon, a two-dimensional boundary, rather than within its volume. The concept was first proposed in the 1970s by physicist Gerard Hooft and later expanded by Leonard Susskind as a resolution to the black hole information paradox, which questions how information is preserved in black holes. Central to the holographic principle is the insight from black hole thermodynamics, particularly the work of Jacob Bekenstein and Stephen Hawking. They discovered that the entropy of a black hole, which measures the amount of information it can contain, is proportional to the area of its event horizon, not its volume. This proportionality is described by the Bekenstein-Hawking entropy formula. This groundbreaking revelation led to the realization that information in our universe might also be encoded in a similar way, suggesting a deep connection between gravity, quantum mechanics, and information theory. One of the most compelling applications of the holographic principle is in the context of the anti-de Sitter conformal field theory correspondence proposed by Juan Maldacena in 1997. This duality connects two seemingly different types of theories: a gravity theory in a higher dimensional anti-de Sitter space and a conformal field theory defined on the lower dimensional boundary of that space. The anti-de Sitter conformal field theory correspondence provides a concrete realization of the holographic principle, where the dynamics of a higher dimensional gravitational system can be fully described by a lower dimensional quantum field theory. This correspondence has been instrumental in advancing our understanding of quantum gravity and has provided new insights into strongly coupled quantum field theories. Moreover, the holographic principle has profound implications for our understanding of space, time, and the nature of reality. It suggests that our three-dimensional world could be a projection of information encoded on a distant two-dimensional boundary, challenging our conventional notions of space and dimensionality. This idea aligns with the principles of quantum mechanics and has led to further exploration in areas such as string theory and loop quantum gravity. In string theory, for instance, the holographic principle provides a framework for understanding how spacetime can emerge from more fundamental, lower-dimensional objects. The implications of the holographic principle extend beyond theoretical physics, influencing fields like cosmology and information science. In cosmology, researchers are exploring whether the universe itself might be a hologram, with all the information about our vast cosmos encoded on a distant cosmic horizon. This line of inquiry could potentially resolve some of the biggest puzzles in cosmology, such as the nature of dark energy and the initial conditions of the universe. In information science, the principle has inspired new ways of thinking about data storage and processing, suggesting that information might be fundamentally linked to the geometric properties of spacetime. While the holographic principle remains a theoretical construct, it continues to inspire physicists and cosmologists to think deeply about the nature of the universe. Its potential to unify the laws of quantum mechanics and gravity and to offer new perspectives on the fabric of reality makes it one of the most intriguing and promising ideas in modern physics. The ongoing research and debate surrounding the holographic principle underscore its significance as a concept that bridges the gap between abstract mathematical theories and the tangible, observable universe. In summary, the holographic principle posits that the universe's information content can be described by a lower dimensional boundary, offering profound insights into black holes, quantum gravity, and the nature of reality itself. Its applications, particularly through the anti-de Sitter conformal field theory correspondence, have advanced our understanding of the interplay between gravity and quantum mechanics, highlighting its pivotal role in the quest for a unified theory of physics. The principle's influence extends into cosmology and information theory, demonstrating its far-reaching implications and potential to revolutionize our understanding of the cosmos. String theory. String theory is an ambitious and deeply compelling framework in theoretical physics that seeks to reconcile the principles of quantum mechanics with general relativity, aiming to provide a unified description of all fundamental forces and particles in the universe. At its core, string theory posits that the most basic building blocks of the universe are not point-like particles, as traditionally thought, but rather one-dimensional strings that can vibrate at different frequencies. These vibrations determine the properties of particles, such as their mass, charge, and spin. In essence, just as different vibrational modes of a violin string produce different musical notes, different vibrational states of these fundamental strings correspond to different particles. One of the most striking aspects of string theory is its requirement for additional spatial dimensions beyond the familiar three dimensions of space and one of time. While we experience the world in 4 dimensions, string theory suggests that the universe actually contains up to 10 or even 11 dimensions. These extra dimensions are thought to be compactified or curled up at scales so small that they are imperceptible to our current instruments. The idea of extra dimensions provides a fascinating new perspective on the fabric of reality, potentially explaining phenomena that cannot be accounted for by conventional physics. String theory comes in several different formulations, the most prominent being Type 1, Type 2a, Type 2b, heterotic SO32, and heterotic E8 times E8. These different versions of string theory are related through a web of dualities, which are mathematical transformations that reveal deep connections between seemingly distinct theories. The discovery of these dualities was a major breakthrough, leading to the realization that all 5 string theories might be different aspects of a single underlying theory, often referred to as M-theory. M-theory, which requires 11 dimensions, remains an area of active research and is believed to encompass all the different string theories into a cohesive framework. One of the remarkable successes of string theory is its ability to naturally incorporate gravity, something that has eluded other attempts at unifying quantum mechanics and general relativity. In string theory, gravitons, hypothetical quantum particles that mediate the force of gravity, emerge as one of the possible vibrational states of strings. This provides a quantum description of gravity, potentially resolving conflicts between general relativity and quantum mechanics at very small scales, such as those encountered in black holes and the early universe. Despite its theoretical elegance and potential to provide a unified theory of everything, string theory faces significant challenges. One of the main criticisms is the lack of experimental evidence. The scales at which the effects of string theory become significant are so small, typically on the order of the Planck length, that they are currently beyond the reach of any experiment we can perform. Additionally, string theory predicts a vast landscape of possible solutions, known as the string landscape, with an enormous number of potential vacuum states, each corresponding to different sets of physical laws and constants. This raises the challenge of explaining why our universe has the specific properties it does. Nevertheless, string theory has profoundly influenced modern physics, providing new insights and techniques that have found applications in various fields, including condensed matter physics, cosmology, and quantum field theory. The mathematical tools developed in string theory have led to advances in understanding black hole entropy, the nature of space-time singularities, and the properties of exotic phases of matter. For instance, the anti-de Sitter conformal field theory correspondence, a conjectured duality between a type of string theory in a higher dimensional space and a conformal field theory on its boundary, has provided powerful methods for studying strongly interacting systems and has deepened our understanding of holographic principles in physics. In summary, string theory represents one of the most ambitious and mathematically rich attempts to unify all fundamental forces and particles into a single theoretical framework. While it faces ongoing challenges and awaits experimental validation, its conceptual and mathematical innovations continue to drive progress in theoretical physics and our quest to understand the deepest nature of reality. Black hole information paradox. The black hole information paradox is a profound and unresolved puzzle that lies at the intersection of quantum mechanics and general relativity, challenging our understanding of the fundamental principles of physics. At its core, the paradox arises from the conflicting predictions made by these two pillars of modern physics regarding the fate of information that falls into a black hole. According to general relativity, black holes are regions of space-time with such intense gravitational forces that nothing, not even light, can escape once it crosses the event horizon. The event horizon is the boundary beyond which all causal contact with the outside universe is cut off. When an object, whether it be matter or information, crosses this boundary, it is believed to be lost forever from the observable universe. This poses a significant problem because, according to the principles of quantum mechanics, information must be conserved in any physical process. This principle, known as unitarity, asserts that the evolution of a closed quantum system preserves all information about its initial state, meaning that no information can be truly lost. The paradox became more prominent with Stephen Hawking's theoretical prediction in 1974 that black holes are not completely black but emit radiation due to quantum effects near the event horizon. This phenomenon, known as Hawking radiation, implies that black holes lose mass and energy over time, eventually leading to their evaporation. However, Hawking radiation appears to be purely thermal, carrying no information about the matter that has fallen into the black hole. If a black hole evaporates completely, it seems that all the information about the infalling matter is lost as well. This potential loss of information directly contradicts the unitarity principle of quantum mechanics, leading to the black hole information paradox. Over the years, numerous proposals have been made to resolve this paradox. One of the early ideas was black hole complementarity, a concept proposed by Leonard Susskind and others. This idea suggests that information is both reflected at the event horizon and passes through it, but no single observer can witness both events simultaneously. This dual perspective preserves the consistency of quantum mechanics and general relativity without violating either principle. Another significant development in addressing the paradox came from the holographic principle. The holographic principle posits that all the information contained within a volume of space can be described by a theory defined on the boundary of that space. In the context of black holes, it suggests that the information about the interior of a black hole is somehow encoded on its event horizon. This principle gained further support from the anti-de Sitter conformal field theory correspondence. This duality provides a concrete realization of the holographic principle and has been instrumental in advancing our understanding of quantum gravity. In recent years, the concept of firewalls has been introduced as a possible resolution to the information paradox. According to this idea, proposed by physicists such as Almhiri, Marolf, Polchinski, and Sully, an infalling observer would encounter a high-energy zone, or firewall, at the event horizon, which would destroy any incoming matter and information. This concept challenges the conventional understanding of the smooth and uneventful passage through the event horizon as predicted by general relativity. The firewall proposal has sparked significant debate and remains controversial, as it conflicts with the equivalence principle of general relativity, which states that an observer falling into a black hole should experience no dramatic effects at the event horizon. The black hole information paradox continues to be a critical and open question in theoretical physics, driving researchers to explore deeper connections between gravity, quantum mechanics, and information theory. Resolving this paradox is expected to provide profound insights into the nature of spacetime, the behavior of quantum systems under extreme conditions, and the ultimate structure of a unified theory that reconciles general relativity with quantum mechanics. The ongoing efforts to solve the paradox have led to significant advancements in our understanding of black holes, quantum field theory, and the fundamental nature of reality. Despite the lack of a definitive resolution, the paradox continues to challenge and inspire physicists, highlighting the profound mysteries that still lie at the heart of our understanding of the universe. Ekpyrotic universe theory. The Ekpyrotic universe theory is an intriguing and relatively recent cosmological model that offers an alternative to the conventional Big Bang theory. Derived from the Greek word ekpyrosis, which means conflagration or out of fire, this theory proposes that our universe was created not from a singular explosive event, but from the collision of two parallel, three-dimensional worlds, or branes, in a higher dimensional space. Introduced by physicists Justin Corey, Bert Overoot, Paul Steinhardt, and Neil Turok in the early 2000s, the Ekpyrotic theory attempts to address several persistent issues with the Big Bang model, including the initial singularity problem, the horizon problem, and the flatness problem. In the Ekpyrotic scenario, the universe undergoes a cyclic process driven by the repeated collision and separation of these branes. Each collision initiates a hot, dense state similar to the Big Bang, setting off a new cycle of cosmic evolution. One of the theory's key advantages is its ability to circumvent the singularity problem. In the Big Bang model, the universe is thought to have originated from an infinitely dense and hot singularity, a point where the laws of physics break down. The Ekpyrotic theory, however, suggests that the universe's beginning was a smooth transition from the collision of the branes, avoiding the singularity and its associated problems. Another significant aspect of the Ekpyrotic theory is its solution to the horizon problem, which questions why distant regions of the universe have such uniform temperatures despite being causally disconnected. In the conventional Big Bang model, cosmic inflation is invoked to explain this uniformity. The Ekpyrotic theory, on the other hand, proposes that the universe had a long, pre-existing phase of slow contraction before the branes collided, allowing distant regions to come into thermal equilibrium before the Big Bang-like event. This pre-Big Bang phase of contraction leads to a homogeneous and isotropic universe without requiring an inflationary period. The theory also addresses the flatness problem, which concerns why the universe appears to be spatially flat, having zero curvature. In the Big Bang model, inflationary theory explains the observed flatness by exponentially expanding the universe, thus diluting any initial curvature. The Ekpyrotic theory offers an alternative explanation. During the phase of slow contraction, the universe naturally evolves towards a flat geometry. The contraction smooths out any initial irregularities in the curvature, leading to the flat universe we observe today. Moreover, the Ekpyrotic universe theory provides insights into the origin of cosmic structures. As the branes approach each other, small quantum fluctuations are amplified during the slow contraction phase. These fluctuations evolve into the density variations that later seed the formation of galaxies, stars, and other cosmic structures after the brane collision. This process is analogous to how quantum fluctuations during inflation in the Big Bang model lead to the formation of large-scale structures. One of the primary challenges for the Ekpyrotic theory is obtaining empirical support. While it offers compelling solutions to some of the Big Bang model's problems, its predictions must be consistent with observed cosmological data. Current observations, such as the cosmic microwave background radiation, the large-scale structure of the universe, and the distribution of galaxies, need to be carefully analyzed to validate or refute the Ekpyrotic scenario. Some versions of the theory predict specific patterns in the CMB that could be distinguished from those predicted by inflationary models, providing a potential test for the theory. In summary, the Ekpyrotic universe theory presents a fascinating and innovative approach to cosmology, proposing that our universe was born from the collision of parallel branes in a higher dimensional space. By addressing fundamental issues such as the singularity, horizon, and flatness problems, and offering explanations for the origin of cosmic structures, it stands as a robust alternative to the Big Bang model. While it faces challenges in gaining empirical support, its ability to provide a coherent and comprehensive framework for understanding the universe's origins and evolution makes it a significant and thought-provoking contribution to modern cosmology. These theories push the boundaries of our knowledge, inviting us to ponder the very fabric of reality and our place within it. As we continue to explore and uncover the secrets of the universe, one thing is certain: the quest for understanding will always lead us to new horizons. So keep looking up, stay curious, and never stop reaching for the stars.